welcome back. So what we're looking at today is 3.1, the in-betweeners. So let's go ahead and jump right in. Hopefully my cat's not going to drive us crazy. So comparing additive and multiplicative patterns. The sequences below exemplify either an additive, which is arithmetic, or a multiplicative, which is geometric, pattern. Identify the type and sequence, fill in the missing values on the table, and write an equation. So we've got these different tables, and we want to take and figure out what kind of sequence is being represented, write the equation, and find our missing values. So the pen function on there is not working, so I've got my whiteboards. All right, so for number 1, we have 2, 4, 8, 16, 32. What's happening each time? 2 to 4, well, we could have added 2, but 4 to 8, we can't add 2. That'd be 6 if we added 2. So 2 times 2 would give us 4. 4 times 2 would give us 8. 8 times 2 would give us 6. So we're multiplying each time. So in this case, our type is going to be geometric. So we have a geometric sequence here. Now, what should come after 32? So 32 times 2 is 64. 64 times 2 is 128. And 128 times 2 is 256. So there are the remaining terms in our sequence. So terms 6, 7, and 8. Now for our equation. Well, it's geometric, so start with the first term given to us. So f of x equals 2 times, what do we multiply by each time? 2 to the exponent of x minus 1. Remember, on geometric sequences, your variable goes in the exponent. Some of you guys are leaving the variable off altogether and just doing 2 times 2. That's not an equation. You have to have a variable in there in order for there to be an equation. So keep that in mind, okay? All right, number 2. So we have 66, 50, 34, 18. What's happening each time here? We're going down. Are we dividing to go down though? No, we're definitely not dividing. There's not a common thing we could divide by to get down there. But how do we take and subtract then to get from 66 down to 50? We subtract 16. 50 minus 16 would be 34. 34 minus 16 would be 18. So 18 minus 16 would be 2. 2 minus 16 would be negative 14. Negative 14 minus 16 would be negative 30. And negative 30 minus 16 would be negative 46. Now, for the type, it is arithmetic, since we are adding or subtracting. We're subtracting in this case. Now, for our equation, remember, this right here, what we subtract by, sorry, that's a little hard to see for you guys. What we subtract by, that is what your slope is. So think about it. Arithmetic equations are always in the form y equals mx plus b. So we're going to have y equals negative 16x plus, well, we need to go back to find the 0 term. So if we add 16 to 66, we're going to get 82. So this is our equation. Once again, you need a variable in order for it to be an equation. Keep that in mind. Once again, some of you guys are dropping off that variable. So this is what you guys are going to be doing on 3, 4, and 5. So filling out the rest of the table, identifying the type of sequence, and writing your equation. All right, for this next part, so use the graph of the function to find the desired values of the function. Also, create an explicit equation for the function. So for number 6, find the value of f of 2. So f of 2, that means when our x value is 2, we want to know what the y value is. Well, in this case, it's also 2. So 2. So when we have f of some number, so when it looks like this represents x value, and we want the y value, which was this. So this here represents, we know what the x value is, the 2 is the x, and we want to find what the y value is. Now, in number 7, it says find where f of x equals 4. We don't have this value right here, so we're looking for our x value this time, and we have our y value. So in this case, we're going to go back to the graph. We go to 4 on the y-axis, and then we go over until we find our curve, which is right here. And then we need to figure out, okay, where is that x-wise? It's 1 off of 5, so it's at 4. So 4. Now, ironically, these are proving to give us the same exact values, so 4 equals x. Now, you're going to do the same thing for 8 and 9. Careful, it's not always going to give you the same value every time. It worked out that way for now, but it won't always do that. So on 8, you're going to go to where x is 6, find your y value. Then for 9, you're going to go to where y is 16 and find your x value. Now, for number 10, what do you notice about the way the inputs and outputs for this function relate? So you will notice, once you finish this, that every 2 y values, or sorry, every 2 x values, the y value doubles. The y value doubles. We could see that from, oops, sorry, I forgot to make that big again. So for every 2 x values, the y value doubles. We can see that from here. We have the f of 2, and we're at 2. We go to f of x equals 4, x value is 4. So we're doubling every 2 x values, because at 3, it's not going to be doubled. It's going to be somewhere in between 2 and 4, so it's not doubled, but it doubles every other. Now, for number 11, it says, what is the explicit equation for this function? Now, the reason I'm doing this is because you haven't seen functions like this very often, so that's why I'm doing it with you. So f of x equals the square root of x, of 2 squared. So this is a curve. This is the square root of 2 to the power of x, or f of x equals 2 to the x divided by 2. Either of those work. So basically what we're doing is we're taking each of our x values, dividing them by 2, and that becomes our exponent that we multiply 2 by. So this is a different equation than we've really seen before. It is exponential though, but it's a little bit different since we have that division in the exponent instead of adding or subtracting from our x value. Sorry, I know the light's getting really weird in here. All right, so the next thing that we're going to look at is finding missing values in the table based on the growth that's described. So you may be saying, oh, this is going to be easy. Well, it is. It's just a little different because we're finding the in-between values. So we're finding the in-betweens, and we're looking at these patterns. So your keyword is pattern for this lesson, pattern. So for number 12, it says the growth in the table is triple at each whole year. So at 0, it's 2. At 1, it's 6. We can see the jump, the multiply by 3. So at 2, we multiply by 3. We're going to get 6 times 3 is 18. So we end up with 18 there. Then for 3, skip a number. We'll do the whole numbers first. 18 times 3 is 54. And 54 times 3 is 162. So those were the easy ones to get out of there. Now, the in-between values it's halfway between. So if we take our 6 and divide it by 2, we get 3. We know that. Then there's 2 places. So we're going to take the square root of 3. If there were 3 places, we'd take the third root. If there were 4 places, we'd take the fourth root, so on and so forth. So we're going to take and multiply this to our original numbers. So 2 root 3. So root 3 is actually what we're going up by in half intervals, is we're multiplying by the square root of 3. And if we multiply 2 root 3 times root 3, we would get 6. So then for the next one, it's 6 times root 3. Then it's 18 times root 3. Then it's 54 root 3. So those are our values. Sorry, I totally forgot to make this bigger. There you go. So those are our values. So because we had 2 places, we had the missing place and we had where the 6 was. That's why we did the square root. And then we just multiply this every single time. And a root times a root is just going to give you the number underneath. That's how we can get 2 root 3 times root 3 to get you 6. Okay? All right. For 13, the growth in the table is triple at each whole year. So once again, we're tripling, but this time we're splitting it a little different. So at 2, 6 times 3 is 18. So we still have the same pattern going on here. We're still tripling. But this case, we have 1, 2, 3. We have 3 places. So for this, we're going to take, once again, 6 divided by 2 is 3. But now we take the third root. So this first one is 2 times the third root of 3. Then we'd multiply by the third root of 3 again. So we're going to have 2 times the third root of 3 squared. So what's in that box is 2 third root of 3 squared. I know it's kind of hard to see. Then we'd multiply by the third root of 3 again. We'd end up with 6. So then it's 6 times the third root of 3. And then it's 6. I'm going to write it down below. 6 times the third root of 3 squared. And we multiply by the third root of 3 again to get 18. And we'd have 18 times the third root of 3. And then the last one, 18 times the third root of 3 squared. So it's just making what we're multiplying by becomes a root, so a radical value rather than a whole number, because we're finding these in between values. All right, so you'll do the same thing for 14, except this time it has a growth factor of 4. So be careful with that. It's a little easier though because it's not fractional. All right, for 15 through 20, simplify the following expressions using exponent rules and relationships. Write your answers in exponential form. So for example, 2 to the second power times 2 to the fifth power equals 2 to the seventh power. So we add exponents when we're multiplying base numbers. So we have 3 to the second times 3 to the fifth. We add those, so we have 3 to the 2 plus 5, which is going to equal 3 to the seventh. Now, when we have division, we're subtracting. So this is 5 to the 3 minus 2, which equals 5 to the first. Now, when we have a negative, we never want to have negative exponents. So the rule is if we have a to the negative first, it equals 1 over a to the first. So this would be 1 over 2 to the positive fifth. So it just flips it and turns the exponent positive. Okay, so those are your exponent rules and relationships. You'll finish the rest of those. So once again, your keyword is pattern. If you guys have any questions, feel free to ask. Have a great day, you guys.